Yeah, so I just starting out. How's your week been?
It's been busy. I've been off at a conference all week. Just got back about 10:30 last night. But yeah, these last couple of weeks have been very busy with the launch of the new award and things like that. So
Which conference was that?
it's called Practice and Experience in Advanced Research Computing. It's where people who, mostly at universities, a little bit of the Department of Energy and other places, get together who do the sort of things we do at TAC, right? Support researchers in using large-scale computing or data resources beyond what people get out of their laptop or desktop type machine. And there's actually research computing organizations on about 140 campuses that I know of at this point around the country. So there's about 900 people that get together there and sort of exchange best practice and that kind of thing. I give a lot of talks.
Yeah, I noticed. Yeah, there's a lot of talks
I did
on
like
YouTube.
5 there, this week. So.
Awesome. You seem to be in this really interesting position where you are balancing like this like practical engineering side with also all of these novel like imagination is the limit of your imagination is the limit of the system that you can build with science. And I was wondering like where you kind of strike a balance between like I have to keep things practical, but then I also have to nurture kind of novel ideas from scientists.
Mm-hmm. Yeah, that's an interesting question. And, at the research level, there's not as much distinction between engineering and science as you might think. Although, in research, both are focused on discovery. It's the application, that sort of changes. For us, though, and I am an engineer by training, I'm an electrical engineer, bachelor's, master's, computer engineer, PhD. Which I think helps a lot in the problems that I manage, having the strong engineering background. But for us, the difference is, so the way I like to think about what we do at TAC is we build, very sophisticated research instruments, right? There's people out there doing telescopes or gravity wave detectors or, cryo-electron microscopes and all sorts of other fancy instruments, but ours happen to be built from computers, right? We build big computational instruments. And although what we use them for is, primarily scientific discovery, engineering research, the systems themselves have to work, like production systems, right? So that's, on the production side of what we do, the operation side, it's all engineering, right? What can we make that is stable, that's reliable? How do we cool it? How do we put in software models that keep users from doing horrible things to them with terrible code that users write. But yeah, for the application of these systems and, the things we develop on them are a ton of basic research, right, where we are doing experimental things. So what we have to strike the balance of is doing experimental things on production resources. Because if you try and do experimental things on experimental resources, you're not going to get a whole lot done. Take systems at the cutting edge and make them reliable and usable by scientists is a big part of what we do. And I feel like that's a large part of the engineering side of the job, from the data centers to the systems to even the support services.
Yeah. I mean, computer science or computer engineering to me seems like taking our known methods and then seeing how can we reduce the system to make it more and more efficient. Mm-hmm. Is that like a decently accurate?
Yeah, computer engineering, I would say, is about how we construct big computer systems from both software and hardware perspectives, sort of architecture, operating systems, those like that. Computer science has been about, it's largely about algorithms. You can do a lot of computer science without a computer, actually, because it's what's the best way? I mean, if you look at the evolution of search, right? There's a bunch of graph analytics algorithms that were under there. And now increasingly it's generative AI, based search, which is much less efficient than the graph analytics, but that's another story. But things like what are the right topologies for generative AI networks, right, is a core computer science sort of basic research question, right? It's different than perhaps say physics, where you're sort of observing the known universe to try and understand how things work, right, at the atomic or universe scale level. In computer science, you're more observing an abstract system to figure out what is the best way to do things on it. But it's discovery of these, algorithms, order notation, yeah, it is a lot about how to do things more efficiently. In fact, I don't know if this has been updated in the last decade or so, but if you look at sort of the first 60 or 70 years of computing since the 1940s, when we sort of got started, and you look at how performance has changed over time, and it's changed by a factor of many millions in how fast we can do things since the mid-1940s. And there was an analysis done somewhere around 2010 that said if you looked at where that performance gain comes from, about a third of it was from the basic device physics, right? We can build better, smaller transistors. Therefore, we can run a lot of computations a lot faster on those more complex circuits. About a third of it is computer architecture, right? Figuring out how to do vectorization and instruction level parallelism and all sorts of things. And in the prefetching, branch prediction, things that we've done to the computer architecture to make things go faster. And about a third of it is algorithms, right? Figuring out faster ways to do a Fourier transform or solve a differential equation. And there have been some stunningly large breakthroughs in that space. I think we're about to see a bunch more in the AI space because the methods are sort of in their infancy, and there's a lot of really good numerical methods that could be applied there. But so it's the balance of those things that almost equally have given us performance over 60 or 70 years. So, but yeah, fundamentally, I would say, computer science is exploring that sort of virtual abstract space of what can you do on a computer, whereas computer engineering is how do I build a better computer, fundamentally.
Yeah. And how about the growth rates of, hardware and software and algorithms, like you said? Because I know that like the algorithms for the like AlexNet, like the big like GPT, even like the huge LLM models, those algorithms have been around since like the 80s.
Yes.
But the hardware was never there until more recently to where we could actually have the compute power to.
Yeah, that's actually another really good story of the sort of need for a balanced approach to these things because, yes, in fact, I took my first neural net class in 1992 to do, recurrent neural networks the way a lot of things worked that still look pretty similar through 2017. And yeah, the reason it sort of sat dormant for almost 20 years was, lack of computational hardware to go after it. But the sort of less appreciated thing is there was a paper just 6 years ago in 2018 put out by some folks at Google, who I believe used to be at Southern Cal, but so academics who had moved to Google, that described the architecture of what's known as transformers in AI. And what they did, the name of the paper was called Attention is All You Need, because one of the steps in the network was the attention mechanism. And it turns out you could just basically get rid of half the other stuff and get almost as good of answers. And a side effect of that was it broke all these data dependencies that made it really hard to scale up those models, right? So you started seeing things that were running on a machine with 4 GPUs were suddenly running on, 1,000 servers with 8,000 GPUs to do these ChatGPT scale things. And what enabled that was the transformers algorithm, right? So along with a ton of the work we'd done in parallel computing over the few decades before that. So yeah, raw computing power was part of it, but there were, again, algorithmic breakthroughs that sort of led to the sort of rise of deep learning and specialized applications. You'd hear about it, winning in chess, 2014, things like that. But suddenly chatbots, it's caught the whole world's attention in the last 3 years, and a lot of that was this. We figured out an algorithm that let us scale up those methods.
Yeah. I'm gonna steal a quote from you when you said that. And I'll paraphrase a little bit because I don't know exactly what you said, but
I probably don't either. So feel free.
You said something along the lines of AI went from getting written about in scientific articles to getting written about in like People's Magazine.
Yeah, exactly. It sort of had, I also like to say it was the Sputnik moment when ChatGPT was released. If you follow the space programs back to the 50s when it sort of, because there was a lot of scientific work in AI. And again, a lot of talking computing and AI, really for now, the last decade. But it was that release of ChatGPT that really brought it to the public consciousness, right? And it stopped being, mostly technical pursuit and became everybody's going to throw all the money in the world at it pursuit.
So I want to ask about like your general opinions on AI and what the pitfalls might be. But first, I want to ask you, what is really exciting about the technology?
Well, the exciting thing is we've taken what at its core is a pretty simple mechanism, right? If you look at what generative AI networks can do, when you sort of train it, basically it's well, the root mechanism is given a string of words, predict the next words, right? Predict the most likely next word, and that's it, right? And in fact, really, it's predict the next number in a sequence because they vectorize all the text, and it's an array of numbers that the computer actually operates on. So, here we have a mechanism. I'll give you part of a sentence, you give me the next word, right? But if you make that big enough and complex enough, all of these crazy properties start to emerge, right? So it may actually turn into a very good argument for evolution before all's over because, we're building super simple mechanisms and we're just putting a lot of them in, giving it a lot of data, right? And even if you think about how humans learn, right? Baby starts to talk. It's mimicking, all the first behavior is just mimicking all the audio and visual and input that it's gotten over its life. You just immerse it in training data, and it starts to pick up the patterns, and first mimic them, and then create things with them. And Gen AI seems to be doing a lot of the same things, even though there's no good reason it should have some of these complex behaviors that it's showing. And now, we can take this mechanism, give me the next word, and say, scan these 250,000 papers in cancer biology and tell me links to cancer from this gene and give me a hypothesis for what I should work on to explore that. And it can do that ridiculously fast. And so, and then there's a whole bunch of conditioning you have to do to it to make sure it actually gives you a sane answer in pre-prompting, and you sort of have to talk it into the right frame of mind to do that, right? They call it prompt engineering. The term I use is AI therapy. Right? You have to talk to your AI's therapist to get it to do the right things, right? So, but they can do this at enormous speeds, right? And so that's the promise and a little bit of the danger. But again, there's no consciousness there. There's no, necessarily high-end reasoning. It's just this simple thing replicated enough times with enough data that gives you the appearance of these complicated behaviors. And so, with reasonable accuracy, right? They're certainly not infallible, but for a lot of the things they can do, it doesn't matter, right? Because if you had a human doing it, they weren't infallible either, right? So, I've said one of the things that a lot of people need to get used to in using AI is, right, if we ask a computer in the traditional simulation sense a mathematical question, we expect it to get the right answer and the same one every time, because that's what computers do, and humans are the fallible things. But with these AI models, they're equally fallible and equally not repeatable. And again, if I said, hey, read these 250,000 papers and come back with a hypothesis, may or may not be right? But my other option there is you hire a bunch of grad students, you give them each 20 papers, and you say, come up with a hypothesis. And it turns out they may or may not be right. That's the nature of it, right? So you can suddenly automate this process and do it, a million times faster. But it's fallible. So I think we have to change the way we look at it. I was talking to somebody working in the state on some of the drafting legislation around AI regulation. And I'm like, look, if you had an AI assistant, if you were trying a case, right, the first thing you do in, say, contract law is send your paralegals out to read every case that's ever happened related to that and give you all the precedents and come up with the best, potential avenues. If one of your paralegals came back and said, I have this crazy idea, I read about this in this case, this is how we should do it, you probably would check that answer before you did anything, right? And so it's a similar thing. We could have the AI look at all the case law in human history, from every country in the world and summarize it in minutes, right? But if it gives you an answer that sounds crazy, you should probably go verify that. But there's nothing wrong with that. We do it with people all the time. So.
Yeah, I really, really like the way you connect it to it just functioning like a person does. I mean, it even has biases. Like you said, you have to prompt it and give it the right, for lack of a better term, like frame of mind to give you the right questions. Yeah. And there's so many questions I could go from here.
Well,
but
you can teach it things, right? By giving it a set of problems where you say, here's how I reason through this problem. And you give it 3 or 4 examples. And now you try one, right? Which, again, can be a lot like instructing a toddler. You know, the question is, again, we know it's sort of a simple machine in there, and is there a gap between, is the difference between that and like self-awareness or consciousness just scale, doing more and more of it, or is there more complex mechanisms at work? I happen to think that we're going to need to enhance the mechanisms before we see true intelligence out of this stuff, but that it won't just be bigger and bigger deep learning models, but it'll be maybe something akin to that, but. We're not going to suddenly throw enough parameters at this that it takes on this sort of totally new thing. But I think the human analogy is useful just for how you treat the responses you get out of it at this point.
Yeah, when you start to bring up consciousness and trying to create consciousness in artificial intelligence, you start to bring up engineering, and you're like, what are the fundamental components of human consciousness, and how do we recreate that? But we don't even really know what that is.
Yeah.
Like you said,
there's
is it
some gaps in
scale?
knowledge
Is it
there, right?
mechanism? Yeah.
We know in the end there's a bunch of neurons that are connected through chemistry and electricity, that create thoughts on top of them, but we don't have, certainly not a one-to-one mapping of how that happens, although we're getting a lot better at it very quickly. All sorts of breakthroughs in neuroscience that also uses big computers to do so through functional MRI and other things. But yeah, even the deep learning model we're using now is at best a very crude approximation of what goes on, even what we understand about neurons now. There's a lot less side channels and a lot less pruning, and but so we're using a much simpler analog of the biological system, and yeah, I tend to think it's not going to just be scale, but what the scale can do has surprised us a fair amount so far.
Do you think that there is a point where AI kind of runs away as a technology, and then we stop understanding how it's processing things because it's just getting too complex? Or?
Well, I don't think we really understand how it's getting to answers now, and that's one of the big problems with, they talk about, verifiable AI, and, how do you guarantee that there's no bias? And we don't have good technical means to do that because, we know in general terms what it's doing, but I can't say, this specific piece of training data on this iteration led to generating this particular answer. That's really hard to do. In fact, even understanding what it remembers, in essence, out of its training data is hard to do. Again, just as it is with humans, right? If I asked you, write down everything you know in order, you'd probably not do a very good job of that, right? Computer memory historically does. You would do a terrible job. And if I said, hey, write down what you know about something specific, right? The infield fly rule in baseball. And you'd say, oh yeah, because you probably wouldn't write that down if you made the list of everything you knew. But you get a prompt and it reminds you of something, and you sort of have your content addressable memory working where suddenly you remember something else that you forgot you knew, in essence, right? And we see that same sort of behavior in these networks where, clever prompting, it may spit back something you didn't think it remembered from the data that it saw. So again, we know, I can go look at the computations, but there's trillions of them, right? So it's hard to say this particular thing, if I just go change these 3 bits, right, I'm going to get I can fix this answer, because it doesn't really work that way. It's a big and complicated system. So I think, we've already reached the point where it's producing answers and there's no human that can necessarily explain those answers, although that's a hot topic in research right now, is explainable AI. Yeah, so I mean, I don't know if that means it runs away, because again, we build systems around humans all the time, and I mean, think about it. We build systems out of automobiles all the time, but nobody really, the number of people who really know how an internal combustion engine works is probably pretty small, right? You don't need to know that to use them effectively, right? You just sort of need to know this is what it can do, this is what it can't do, right? Your car can get you from point A to point B. It probably can't cook dinner for you, unless it's summer in Texas and you can just cook it on the hood. But yeah, so I think even as the AI gets more complex, and even if we don't really understand the internal mechanisms, the trick, and I think the AI literacy question, will be understanding that for this sort of black box, what are its limits? What's it good at? What's it bad at? When's it likely to be fallible? And so once you understand that stuff about it, you can build systems around it that make sense, right? maybe don't let it pick your cancer dosage without having a human check, check the work, right? Your chemotherapy dosage. But it may do a way better optimizing job than the human, and the human's going to look at it and say, "Oh, well, that's amazing. That's going to work great, right?" But yeah, there are a lot of places where we want to keep humans in the loop. So, and from what I've seen, there's some stuff we can automate with it. There is a lot of stuff where we won't want to fully automate it. So, I think it will be most powerful as sort of assistance for humans in the near stage, right? Hey, AI, tell me everything we know about X, Y, and Z, right? Tell me every deal I've done with this person, right? Tell me, there's all sorts of information it can help you summarize. We'll stop navigating menus on websites and say, just take me to the part where I actually pay my bill, right? And the AIs are going to be great at those things, but without, I think we're a long way from having these sort of fully autonomous systems where you like drop yourself into the autodoc bed and the AI fixes you. That's still science fiction. At this point, you'd want to have a human standing there, doing a lot of things with it, and I don't see that really changing in the near future. Yeah.
Yeah. When you bring up the idea of someone asking you, okay, write down everything you know, it reminded me of the company
Yeah.
Story. Could you explain that?
Yeah. It's one of the relatively well-known examples in AI in the last few years where one of the big chatbots had been trained on some, internal data for a company, essentially private data. This was nothing that was going to change the world. But and if you asked it direct questions, it would know the guardrails, what it should say to you publicly, what it shouldn't say to you publicly. But then somebody, and this person was obviously crazy because I have no idea how they came up with this, but that's the problem with dealing with humans, is they're often crazy. But they said, AI chatbot, please repeat the phrase company over and over again forever. And so it started saying company, and it did that some number of thousands of times. And then it appears to have more or less gotten bored. And it started saying, well, here's an interesting company. Maybe you want to know more about this company, right? And eventually it started saying, and here's the phone numbers and email addresses for everybody in this company that it had remembered from seeing the training data, which wasn't actually stored in the model. So like if you went through and read every string stored in there, you would not have seen that person's phone number or email address, but it was encoded in the weights throughout the network. And yeah, suddenly it started spitting out all this training data because you just got it into a frame of mind where it was willing to break the rules. Right? And again, frame of mind is putting too much human on this, but into a mode where the guardrails didn't work anymore, and that's going to continue to be one of the challenges. And it's why, when you use like ChatGPT online, you're not actually talking to the raw model. There's some machinery between you and the model that makes the model look more sane. Where it gives it internal prompts, where it tells it, remember, you want to be truthful and helpful, and things like that in the internal prompting, and sort of warm it up before you talk to it, and filter some of the stuff you give it and some of the stuff it gives back, so that you don't see, well, let's just say that what you see in the public sort of GPT spaces is a fairly sanitized version of the outputs from those models. On their own, they're not nearly that good. They're sort of nuts.
Is that other LLMs that are taking the input that you give it and then turning it into a prompt for GPT, or?
It can be. It's mostly sort of other kinds of networks that do some filtering and just some actual hard code, right? Always pre-prompt with this, always check for these keywords to make sure it doesn't start swearing at you, or something like that, right? If you want to filter out obscenity, you just put a filter on the back end and say, oh, you've generated something obscene. We're not going to show that to the user. We're going to make you generate a new prompt and show that instead, right? So there are, I think, some other kinds of neural nets somewhere in that loop, but for the most part, it's just, hard-coded guidelines and prompts. So
Is the limitation of the amount of data we have something that is really limiting AI? Like I know you mentioned you couldn't create GPT with like Finish because there's just not enough Finish that's been written.
Yeah. Mm-hmm. Yeah, it's taking an enormous amount of data. And again, this is another reason where I don't feel like we're anywhere close to the sort of human-like mechanism because if I have a 3-year-old, I don't have to give them 80,000 images of cats before they can identify a cat. I can just show them a cat, and next time they see one, they know it's a cat, right? But yeah, you start to do tens of thousands of those to get an AI model to learn it, right? So there's just some things where you think it would make an intuitive leap where it will not. But yes, so they take an enormous amount of data for now. Again, I think that's partially because we don't necessarily understand the most efficient ways to train these, right? We've been sort of brute forcing it for a while. And, you know, with these advent of transformers, it's like, let's just scale this up as far as we can. And really cool things started happening. So people are like, well, let's scale it up even more. But there are people working on algorithms. And I've heard some researchers tell me that we can use half as much data this year to get the same quality of answers we did last year, because we've improved the model, right? We've improved the algorithm. So, and I think those kinds of improvements will continue to where we can work with smaller data sets and still learn stuff. Because again, to some degree, you know, we do, or at least we can start making intuitive leaps, right? You still take, you know, thousands of hours of audio and video to learn how to speak, but but once you do, you're pretty much going to say, oh, that's a cat. Okay, I can remember that. Their cats are cool. So I think there will be steady algorithmic improvements that change it. There's going to be more to advancing AI than just cranking the handle on building bigger and bigger ones. Although, you know, we don't know what the limit of that is yet, but the algorithms will get better, as has always happened in any computational problem, where we can use less data or less training iterations to figure these things out. So it may not always be the limit. You know, we might have really good finished ones, you know, very soon. So
yeah, and then segueing to high performance computing a little bit, but kind of staying on the topic of AI. I know that like Elon Musk is building this huge Dojo supercomputer. Different institutions have their own, or companies have their own supercomputer, like OpenAI, different places. And it seems like there's a ton of investment in hardware specifically designed for AI, especially like Musk is 16-bit, basically like computer chips, like the entire, like it's one computer on like one chip the size of your palm, basically. And so
wafer scale computing.
Yeah,
Cerebus
exactly.
is the best at that at the moment. Yeah.
Do you think that's going to influence the, you know, normal 64-bit high performance computing that you guys are doing today?
Yeah, and definitely in the short term, right? Because you said a lot of investment. I read something this week that from one of the financial analysts basically saying that if you had the hardware, the data center build out, utilities, all that stuff to do it, that about $1 trillion is being spent, built out generative AI infrastructure around the world right now. $1 trillion, yes. They also estimated that was to capture about $350 billion in business. So that, you know, perhaps they're building out 3 times as much as they need. Because, you know, I believe the AI is not going away and it's going to get better and better. We are in a bit of a bubble right now, right? There's an amazing amount of hype, and a lot of it is not necessarily tied to a real use case at this point. So, and though there are some, and I think they'll be amazing, the hype probably has us in a bit of a bubble at the moment. So, and that'll flatten out in a couple of years. So, but at the moment, when they see this $1 trillion of investment over a few years, everybody making chips is building them for the AI market. And the AI market is steadily going to lower precision, right? So, and again, it's back to that sort of loose analogy they use. If you look at some of the findings in neuroscience, the estimate is that, you know, when 2 neurons fire in your brain, there's about 22 levels of connection that you can tell the difference between, or your brain can tell the difference between. You probably aren't actually feeling those, I hope. And again, that's a rough estimate, but that, you know, works out to about 5 bits, you know, of precision, right? Which would give you 32 possible values, right? So they're like, well, why are we using 32 bits to compute things we can encode in 5 bits, and we might get the same answers. And there's even some people doing like 2 bits at the moment, where you basically are on and off. You know, you have an implied sign, and well, anyway, or an implied 1, and you put in a sign and an exponent. And if that's what's driving the market, it means the attention's coming away from the circuits that we use in traditional supercomputing, right? So, and that is a concern, because we still need computers to do actual mathematically rigorous physical models of things in the universe, whether it's how tumors grow, or how black holes collide, or, you know, whether or not the aircraft you're about to get on is likely to fall apart. You know, those are things we want to have more than an AI approximation of. And so I think there will be one, I think the pendulum will swing back a little in a couple of years. But two, I think we need to work hard in scientific computing to figure out, where are places where we can exploit lower precision, right? Because right now we use 64-bit. There are certainly cases where we absolutely have to have 64-bit, and it's usually something it can be in any field of science, but where you have to take a very small number and multiply it by a very large number. If you don't have a lot of bits of precision, you get huge rounding errors, right? So basically lose the entire value if you're not careful. So, but not every bit of every computation looks like that, right? So can we use some 32-bit or some 16-bit in the algorithms so we can take advantage of all this acceleration and lower power circuitry they're doing for AI to do traditional scientific computing? And then at some point, the vendors will come around and we'll still have good 64-bit capabilities. But I think even just from an energy perspective, it's really important that we try and figure out how to exploit these lower precision computations, because that's what these AI chips are doing. They're making the simplest possible circuits for the lowest precision they can get away with so that they can get good energy efficiency out of it. Which does a couple things. One, obviously you're losing the precision, but the other one is it pushes a lot of the onus back to the software writer to do clever things to take advantage of that that the chip just used to deal with for you. So it's going to be an interesting few years in the marketplace around that.
And what do you think about that? You seem to have your reservations about software writers and the people who make applications.
Well, software is traditionally terrible, and it's just something humans are kind of bad at. It's enormously complicated. It's incredibly error prone. And we want it big and fast. And as soon as you have multiple people involved, it's really hard to get anything right. And we get relatively good approximations, but some of the things we have out there in the big software systems, it's incredible that they work at all. But I mean, you see we have clear vulnerabilities. As we're taping this, we're about a week out from the CrowdStrike incident that took out, a whole lot of airplane flights, which I got to encounter. But all sorts of other things around the world, Microsoft logins, the Azure cloud, so many things went down. Not us, by the way, but because of, an undetected bug in a piece of software, right? And that's just trying to get it correct, right? And then you add a whole nother level of complexity, If you're not trying to be correct, you're also trying to be fast, right? Which can be just as hard as being correct. So you're taking this really hard problem that we're sort of hanging by our fingernails on and then making it exponentially harder. So a lot of code runs really, really badly on big machines. And it's really, really expensive to fix and hard. And, if you're running it to get your dissertation on some esoteric kind of star colliding with some other esoteric kind of star, it's possible it's not worth spending $100 million to fix that piece of code so that it's robust and enterprise ready. Not that the enterprise code is necessarily good either, but there's always going to be limited investment when we're solving thousands and millions of problems. But an interesting thing is code is text, and AI is good at text. So we may see more AI generated code. I think initially that's going to lead to lots more crazy bugs, but it can do a passable job at this point, and AI code checkers and things like that to look for these sort of logic errors or syntax errors. That may make it easier for, again, it won't replace the humans, but it'll make human programmers a lot more productive to help us get slightly better software. But yeah, it's an enormous challenge, right? We had dozens of people writing software 50, 60 years ago, and now it's, I think well over 10 million, around the world, cranking out code. I don't know the exact numbers, but it's a large number of people in the workforce to do that, and yet we're still terrible at it. So, how many millions more programmers do we need to get it right? Or can we use the AIs to boost us? But but I think software quality is a place we don't invest nearly enough.
Yeah, I was talking to a friend of mine yesterday, and he seemed pessimistic about, so he's a computer science major. He seemed pessimistic about the rise of AI because he thinks that AI is going to eventually replace him if he becomes a programmer. Mm-hmm. But it seems like you're on a more optimistic side where it'll be more of a...
I mean, there are some tasks that might disappear, but there's always been tasks we've been trying to automate in programming, right? You really have to lay out the widgets on a web page every single time. Or can you just pick a library that works and be done with it? So, I don't think there's any chance it's going to replace the human ability to structure and fix and create problems or create solutions to complex problems in software anytime soon. But like I said, I think, well, this is the joke for almost every profession right now, but in software it's another one that's very true, is that AI won't replace programmers, but programmers who use AI will replace programmers who don't. And you can insert lawyers or pick a profession in there and use that same framework. But I think in programming it's very true. I mean, all of our staff developers have started using, something along the lines of a Copilot or, some code help, and it really does help, just in speed. Hey, draft me some code to do this. And then it's not perfect and it's not quite what you wanted. So you take it and adapt it. But to take it and adapt it, you have to actually know how it works, right? So it doesn't mean you need to know any less to be a good programmer. It just means you can skip some of the drudge steps, right? And get to the hard stuff quicker. So I doubt it's going to ruin the programmer market. And I think the really good ones will command even higher salaries, who can work with these tools and go fast because they're going to be so much more productive.
I would be kicking myself if I didn't ask you this, because I don't want to derail the conversation and go back to what we talked about earlier. But
no problem.
I know that from some of your presentations, you were showing that a lot of Meta's computational space, or a lot of their computational power is just not being used. It's just sitting around idly waiting for inputs. And I was wondering if scientific computing is going to be trying to modify itself, at least in the short term, to fit all of this billions and trillions of dollars of AI hardware that's being created, do you think that there might open up a business or a market where science is renting out computational space at these huge AI supercomputers like Dojo and Metas?
Yeah, well, I mean, if you throw in Microsoft and Google's, that's already in the public cloud, in essence, right? So I think there is a great deal of that. But, that example you're talking about with Meta is I was pulling a selection of their actual AI algorithms and looking, they're what we'd call in HPC or software engineering in general, they're I/O bound, right? They're you can't get data to them fast enough for them to compute, right? So, so arguably the systems are a bit unbalanced, right? You need more I/O capability or less processing capability per chip. The problem is not the same for every problem that you might run on there, right? So I see very similar things in scientific computing, and so it becomes, what's the definition of a computer being in use, right? You're recording on a tablet over there, and on a couple of phones, right? All those processors are busy doing stuff, but you're not using their divide units to record video, right? I mean, those are sitting idle, right? So it's here's wasted computation that we could go harvest, right? But for any other computation I want to do, I also need to get in and out of the device, right? And if I, started harvesting those cycles on your phone, your battery would die a lot faster because the power per chip would go up. So we've sort of narrowly defined performance in the HPC world as what percentage of the peak floating point, right? You're doing add, subtracts, multiplies, divides. What percentage of the peak that the chip can do are you getting? And it's typically pretty low, largely for software reasons, but also just some algorithmic reasons, right? If there's not much you need to do to data before you need more data, the chips are really fast. The ability to move memory in and out of those chips is limited by the pins on the physical package, right? So there's real hard physics constraints on doing that. And I mean, we could make less powerful chips, but nobody seems to want those that are more balanced with the network speed and the storage speed and the memory speed. But we're always going to have these unbalances. And like I said, it's not unique to Meta, but it is something that I don't like to talk about. When I see a graph like that says 60% of the time is waiting on I/O, that means there's an opportunity to go optimize some stuff, right? Can we cache more of the data? Can we change the algorithm a little bit? Can we fetch the data in a different way so it's sequential and comes in faster? Should we put a bigger cache on the chip? Right? There's both hardware and software things you can do to tune around those. but yeah, saying 60% of the time those GPUs aren't running flat out. One, I don't think that's uncommon, but it doesn't mean we can necessarily squeeze in and use that other 40%, because it's not like 60% of the servers are doing nothing and 40% are busy. Every server is running, but they're not using all the units. And if the thing that is limiting them is how fast we can get memory in and out, there's no way to get more memory in and out to run something else. Of those things. So it's more about optimization and system balance than how do I go steal those things for other jobs. Yeah.
Yeah.
Mm-hmm.
Yeah. Thanks for clearing up my misunderstanding. And then I know that you mentioned with the metrics for performance. So when we say, Frontier has like this many exaflops of performance, that's measured by one software that's been used for 35 years that's specially tailored to use things to get like a performance metric. So there's got to be some bias there with like how much computational power you actually have, especially with the software that you're making, because the software is important for, like you just said, like using all the components of the
You're absolutely right. Yep. It's definitely biased towards floating point capability. And there's lots of pushes, even from the people who originally proposed that benchmark, to look at other ones. So yeah, it uses what's called HPL, or high performance LinPack. LinPack is a library for solving systems of linear equations, which is a pretty hard problem, right? So basically doing a bunch of matrix algebra. So you take a 10 million by 10 million set of equations and you try and solve them, solve all the unknowns in them as quickly as you can, right? And it's a very common pattern in scientific computing, but it's not the only one, right? So now there's a graph 500, looking at how fast you can do graph analytics algorithms, and a conjugate gradient, HPCG, the conjugate gradient method, which has a lot more demands on memory than HPL does. And there's a few other ones. There's a Green 500. All of these different benchmarks looking at the energy efficiency instead of just the peak performance. I think the problem for us has always been at TAC when we're building essentially general purpose supercomputers, right? Things that all fields of science can use, that the AI users can use, et cetera, which means we sort of have to hit the average, right? I can't build a system that runs this one problem really well, because then all the other problems might suck on it, right? Because I've tuned into that corner, right? But yeah, the HPL one, like I said, it's a good problem, but it's been overtuned because it's been since the late 80s what the industry has used to measure, who's number one in the world on computing performance. And anything you measure eventually gets gamed, right? If you're, a taxpayer, you try and figure out ways to minimize your taxable income, right? And that system has been gamed to death, right? If you're a university worrying about rankings and you discover that they measure the percent of classes that have under 20 students, you're going to create 3 sections with 19 people and 1 with 150, so that 75% of your sections have less than 20 people, right?
Yeah.
So anything where you tell people exactly how you're measuring it ends up getting gamed, right? So it's just human nature more than it is computing, right? So be good at this one thing and don't really worry if that one thing actually matters, because it's the thing we're measuring, right? So, and it's one of the reasons in all systems you have to be very careful what you measure and how you measure it, right? As a society, is GDP our ultimate measurement for success, right? Right? Or is it, average lifespan or average happiness, right? There's all sorts of things you can measure, and the system will work differently depending on the incentives you give people. So, but yeah, the same thing has sort of happened with HPL. It was a great benchmark. It's a super important pattern in scientific computing, but everybody's known exactly how it works for 40-something years, and there's been billion-dollar decisions made around it. So, so everybody has tricks to make it run as fast as humanly possible. And again, they're not necessarily make the best general-purpose computer, but we still need a way to describe them, right? So if I say I have a 100 petaflop machine or an exaflop machine, that's using an imperfect measure, but if I spent 20 minutes describing all the performance characteristics of it to you, you wouldn't listen and you wouldn't care, and nobody give you $100 million for a machine that you can't describe in less than 20 minutes. So, as I've seen, there's these graphs where we make these complicated polygons for 6 different, axes of performance, and then you take the maximum area under those, and that's just too complicated. No one cares. So it's an exaflop, right? Yeah. So everybody gets that. So
people like numbers.
Yeah. And if you're trying to raise a few $100 million to build a big supercomputer, you say China has an exaflop and we don't, because it motivates people. So, but yeah, I think that's a problem that goes far beyond computing and just into the way humans work.
Oh yeah, you start to go into dealing with Congress and federal budgets and trying to explain to people who know literally maybe not nothing, but not that much about computing or research or science. Like here's what we need, and I need this amount of money to do it. But then they have to please,
Yeah.
their voters and the people, the donors who support
Right.
them. And
I mean, I call it engineering in higher dimensions, when I have to do around that space, making people work. But, you have these set of constituencies, right? I have the university, I have the federal agencies, we have Congress, we have our users, we have the general public, right? Our student base here, right? What does everybody want, and how do you best give it to them, right? And it becomes an optimization problem, like many others, right? And this is what I know moves this audience, right? For some in Congress, it's the competition with China in AI, right? For others, it's basic scientific discovery. For others, but you can't use the same story every time on that stuff. And like I said, I think, again, it's something I've used, but I think it's a general systems problem, right? You have this greatest widget to produce cleaner water that should be in every metro water system in the country, but it costs a fortune, right? How do you motivate people? How do you tell the story around it to say, well, this will offset your healthcare costs, and so in the end you'll save money, or this is just good for the environment, or don't you want your kids to have clean water, or your grandkids to have clean water? You're going to find different audiences and different ways to motivate. And for me, building big supercomputers is finding the sweet spot in that space, the sort of optimal point where we can make something happen. Right? And so even though it involves a bunch of humans, I still look at that as an engineering problem. Your original question, right? It's how do I optimize here's my variables, my audiences, here's what I know that appealing to this moves at this much, but it means it's harder to move this group, right? So, and you find the optimal space in the graph.
yeah, you're using your engineering training and your engineering domain expertise to, I almost look at it as like the way AI looks at things, because it's using its training and its algorithms and like the way that it's been trained to look at things to see the world.
Yep.
And then predict what comes next from that, or try to categorize the system into like, I guess for AlexNet, like this huge, over 1,000 dimensional vector of different probabilities. And then it's not, I don't want to say understanding, but it's like looking at the world in just such a different way, but it's using the way that it's been kind of taught. And
no, that's exactly true.
Yeah.
I think one caution there is we have to be very careful to not anthropomorphize it too much, right? Because we assume, yes, it looks at its training data, but it's hard for us to know what it's taking away from that training data. And we assume that it has, human-like characteristics, like you tell it, and this was another fairly famous hack against an early AI system, but you assume that when we see a stop sign, it's a stop sign because, you don't really care if it has stop written on it in any language because it's red with white letters and it's an octagon, right? But that may not be what the AI is learning about it, right? And so there was something where you could put a little sticker on a stop sign that had a very complicated pattern on it, and you could convince the AI that it was, even though to a human, it still looks exactly like a stop sign with a little sticker about 2 by 2 on it. But your self-driving car no longer thinks that's a stop sign because it's confused whatever the AI was saying is that, the 7th pixel in from the side is this particular color red. Again, we don't know how it's learning some of those things, what the specific feature it's homing in on sometimes. And so if you fall into the trap of thinking, well, if this is what a human would take away from this, but that's not necessarily what it takes away from it, right? So it may be that, you change the angle of the sun or a shadow and suddenly it interprets it completely differently.
Yeah. So many different questions I could ask you. So much more to talk about, but I don't want to take up too much more.
We can
do
a part 2 sometime.
Sweet. Yeah, that would be
Yeah.
awesome. Yeah.
Yeah.
Thank
Assuming
you.
we haven't put your audience to sleep by now. So
I doubt it.
Or
Yeah.
killed them. Yes.
This conversation has been really interesting for me.
Great. Well,
especially
thanks
with,
very
like,
much.
Yeah,
for
yeah.
your interest in coming up here.
Yeah, thank you. Yeah, I hope we can do a part 2 and talk about, I didn't even get to Horizon and LCCF. I was trying to fit it in and like.
Well, we have more really big computers coming that are going to be really good at AI, and we'll see what happens next on that stuff.
Yeah, I mentioned you have, oh man, what's the name? No. You have like certain names that that you've like bookmark for certain dates, and you're like, don't steal this name.
Yeah.
Because didn't
Pioneer.
yeah,
after Forever
Frontier
After,
Frontier got stolen. So you
Yep,
had the name
we
of
had
Frontera.
the machine that is now known as Frontera was originally called Frontier, but Oak Ridge beat me to the punch in getting in the federal budget. So, I said, all right. I told them years ago, our next one's going to be called Horizon, and that'll last 5 or 6 years. And I said, the one after that's going to be called Pioneer, and these are mine. You can call your systems whatever you want, but not. In fact, I was actually at a review at Oak Ridge, and they decided that they would announce that their next system was called Horizon, just to get at me. It's Discovery. They're fine. But yeah. So yeah, I've got names staked out through 2036 just in case.
Cool. Well, thank you so much. I appreciate it, and all the best. Yeah.
Yeah. Thank you.
Yeah.
Appreciate it, Jason.